it is kept on this receiver antenna. It is going to receiver antenna. We have a coil. It is going to give some voltage, right, to power this IoT node. Okay, so it is an mostly we can say point to point. So we can see this depends upon RF generator. We can have a length. We can have the length or increase in length. So for example, if you have an fast stack ID, so you can see it is around 5 to 6 meters. We can have it, and you have any ID card or entry card. It is very centimeter level. So it depends upon the generator thing. Okay. Now let's say everything at last come into the square centimeter. So what is the square centimeter you can make it? Let's say you can't have 1 meter square. You can't say that. We can't say that yes, I'm going to generate 1 watt, because we know that IoT device is very small in size. For example, if you take electromagnetic EM, so for centimeter square, it is around 1 microwatt per centimeter square. This is electromagnetic radiation. And radio frequency, it is around 10 microwatt per centimeter square. Thermoelectric, around 10 power 3 microwatt per centimeter square. PV is around 10 power 2. Is indoor, and outdoor is around 10 power 4 microwatt per centimeter square. This is a stress strain and a vibration. So these are one of the things how it is going to. This is a stress strain, we can say this is a piezoelectric, right? It depends upon the thing. So it is kind of electromagnetic. This is RF. This is a thermoelectric. This is a photovoltaic. We can say mechanical. This is common to the piezoelectric. Now, what are the conventional harvesting transducers? What are the characteristics? For example, if you take an light, right? If you take a light, then it is conformal to the small surface area and wide range, and the impedance is low kilo ohm and tens of kilo ohm. So these are typical voltage like this. Then what is the cost, normalized cost, typical power output? From this we can use it for our application, right? Whether thermal or thermal or vibration light, everything we can use it. And these are some suitability. For example, if you take, this is a home thermostat, it can be used for wireless Bluetooth radio, and energy transducer can be solar. Indoor air quality monitor, it can be going to monitor CO2, CO humidity and temperature sensor, it can be solar. Fitness band monitor, accelerometer, thermometer, it can be used for thermoelectric and solar. Smartwatch, it's going to power the CPU, real-time operating system, radio, MEMS, other sensors can be solar. Some of the indoor lighting control can be solar or electromagnetic. Medical patch, solar or electromagnetic. And we can use a water meter also. So you know that there is a water meter, there is a turbine. It can also generate some voltage. It can be used, and it can be used for thermoelectric, making the difference in. And outdoor sensor, the humidity and temperature sensor, wireless transmitter, solar and electromagnetic we can use. Animal monitoring, we can use various sensor, GPS, solar. So like this, everything is used according to our application. We can use different energy transducer, and whether it's good fit for an energy harvester. If it is why, then why not? We have to see like this. Yes, so everything is yes, but only thing is you have to ensure that let's say if you mention this water meter, so if you place a thermoelectric, so you have to maintain the temperature difference between the top and bottom plate of the thermoelectric material so that you can get some voltage. That is important. Like this, you have to see everything. And then what is the workflow of energy harvesting? You have a transducer. It may be piezoelectric, photovoltaic, inductive, and RF. And here the energy processor. So most of the things, though it is going to give AC, because if you take solar thing, it is going to give is DC solar. If you give piezoelectric, it is going to give AC. And if you take RF, our energy harvesting giving to AC. Whether AC can be storable or it can be used directly to power the IoT node, I like to hear. So can be used to charge the battery or power the IoT node? That is possible?
Yes, sir.
AC not possible. We have to convert it into
DC.
Okay, so that is going to happen in the power conversion. And again, let's say we need to be careful about power management also. We can't give more power management and energy storage. So we should be very careful about, because while charging the battery, we need to take care of the power management, and we need to go into the processor and wireless transmitter and sensor, all those things are involved. So these are one of the things required. And if you take a mechanism various energy harvester, so here kinetic AC or thermoelectric radio frequency, kinetic is AC, thermoelectric radio frequency, and photovoltaic is a DC. But after radio frequency, we need to do the rectification, and we have an energy harvesting transducer. It's going to give AC voltage. Then we are going to rectify. Then again, we need to have a DC to DC converter. It may be an buck boost, right? Buck boost, and we need to go to energy storage. It may be a supercapacitor or battery. Then again, we need to give the DC to DC controller. Then again, we need to give the output and load, right? This is the process. So whatever it is coming, we need to do some energy processing. You know that already DC to DC converter. We have seen buck boost, and boost, right? We're going to see that. So these are the important things we need to know. And sometimes, for example, if you have a PV cell, and it depends upon the energy available, right? Power management unit. If the energy is more, you can directly charge the battery. Otherwise, if you want to directly connect it, you can connect to the electronic circuit, right? It depends upon the power available in the PV cell. The power management unit going to take some decision whether it can get the power from directly from PV cell or from the power management unit. So what is the power management unit connect? It is having power processor plus the power process is not a processing power. It is a DC to DC converter, AC to AC converter. So this is again a battery, right? It is having like that. Now these are some multiple input, single inductor, multiple output, right? So that is the thing. So if you have you have a light, you have a heat, biofuel, and you have battery management, small form factor, and you have a sensor and processor and radio, right? Here also typical demand pattern of the wireless device. So first we have to understand how much power is required. In ideal case, we can see there is a less power is required. Sorry. So here in a processing, ideal case, what is the power required? And sensing, what is the power required? Processing, what is the power required? And in transmitter and while transmitting the signal, receiving the signal, what is the power required? We should know all those things, right? So we can see this is the power average required by the system, and this is the average of single input transducer harvester. This is the power average of multi input harvester. So always we know that the average power of the system should be more than the average power, lesser than the average power of multiple input harvester. Then only can supply and it can charge the battery. Okay. So again, it is replicated here, light and T, G, B, F, C, and accordingly, whenever it is there, whenever light is there, we have to take the power. So it is multiple input, single input, multi output, right? It is directly connected to. So whenever the power is available, the switch is connected and it is going to process. So how it is thing. It is an, for example, solar cell. If you're taking as a solar cell, and most of us know it is in PV cell and photovoltaic cell, and we have a MPPT power controller converter who is in here in electrical department. They will well versed in. So maximum power point tracking. So we can't take the power as we need, right? So there is a limited amount of current we have to take when the to achieve the maximum power drawing from the solar cell. We have to use the MPPT power converter. Accordingly, we have to use the voltage regulator and electronic circuit energy storage here, right? And here, what is the passage? Then we have two types of mainly we have two types of solar cell. One is monocrystalline and is amorphous. So in passage, what is the power microwatt per centimeter square going to get? It is depends upon these are coming under the amorphous indoor. This is a monocrystalline, right? Monocrystalline. So monocrystalline is going to give more power output. Depends upon where it is placed, whether it is direct sunlight or passage or general lighting or recreational play, all those things. Okay. And here, energy harvesting from the movement. Let's say from the movement, how we can harvest the energy. So mostly from the movement, we can take the piezoelectric effect, electrostatic triboelectric effect. What is the triboelectric? By friction, we can generate some power. That is a triboelectric. Electrostatic is also by friction. Some charges are, we know that maybe in childhood days you have to take some comb and rub on your head, and there is some electric charges are produced like that. And electromagnetic induction. Let's say if you have a magnet, you have a coil. Then if you move the coil or magnet, is the EMF is going to generate on the coil, right? So like this, what are the things? Let's say small micro oven. This is the milliwatt power. And the drying cloths dryer, this is the milliwatt power, and this all those things is giving different thing, right? This is the electromagnetic energy harvesting, depends upon the diameter we are going to get it. A car engine, large processing machine, so accordingly it is again G, right? G is then gravity, otherwise the vibration intensity, which is going to the unit of the vibration. So it is giving only microwave is going to 0.1, and cloth is around less than 1. This is again blender casing less than 1, car engine giving 1 G, and this is around 10 G. So accordingly, we have to produce the power. And this is for thermoelectric. So we already know that is a Seebeck sensor. So we have an thermoelectric sensor. It is we have to measure the we have to keep the differential temperature. Then we are going to get the output. So this is a differential between hot and cold. What is the milliwatt per centimeter square power is we are going to achieve? Okay. That is the thing. Then again, these are some of the things. The gelatin also can be used for power of wearable and IoT device. This is from Chris Edwards and Southern University Science and Technology. So they're using the thermodiffusion, thermogalvanic, thermogalvanic, gelatin. So all those things material they use. Then they have done some. What is the milliwatt per Kelvin? What is the Kelvin is the temperature? What is the temperature difference? What is they going to get? And we know that in the ambient itself we'll have so many electromagnetic waves. Let's say for example Wi-Fi, RFID, mobile phone networks. From there also we can have we can do it. Otherwise we can have the this is a transmitter, which is an this 1, 2, 3, and we have a controller and sense and AC to DC drivers. That power can be harvested. Again, it can be transmitted to the power, and communication is happening between here, right? So power is harvested from here, and again it is transmitted through the again wireless manner. Then it is powered by we are getting power, and we have a voltage conditioning, all those things we can do. And some of the things, if we are eligible, we are let's say we have provision to keep all those things also here, it is okay. Otherwise we have to do like this. And these are the one of the Chargetech Anthano group. They holds an it is an inject printed prototype of wave harvester, so it can be used in a 5G network, right? And these are the available in the market. For example, ST. This is a evolution board from STM. So this is then a transmitter, and this is a receiver. So you can transmit and you can receive some energy. So these are coils are used for transmitter. These coils are used to receive. You can have it. So this is one of the evolution board. We can try it for our application. Right. So here also they have done with an with the 10 variables and a user with wirelessly they have done. So some of the users are available. And this is again one of the design PNP133. This is a power design. This is from Texas Instruments. This is also one of the reference device. We can use it for the wireless charging, right? So here, let's say for example, one of the application is biosignal monitoring. The patient with elderly patients can be embedded with can wear the clothes which is embedded with the digital biosignal sensor, and it is always having an transmitting getting power from the some power harvesting sensor, whether it's with the thermal trigger RF, and it is going to send the mobile phone, and it is the signal is again sent to the caretaker, right? And this is one of the things. TNEG, a thermal electric nano generator. So they have attached here, and while bending, what is the voltage is generated, right? So while bending 30 degree, what is the voltage? Approximately 60 degree, what is the voltage? 90 degree, what is the voltage is generated? And we can, after this, we can do the rectification. Then we can use it for our power. Okay, powering the IoT node. And this is again polymer and metal. This is one of the sensor flexible array, which is again having multiple sensor. From this we can generate the power, and it can be given to the IoT node. So this is one of the thermoelectric. So if you use an power source hybrid techniques, the production of energy at higher levels. Disadvantage is the power management module we usually require to in system architecture. If you use an so many modules, then what is going to happen is going to be complex, but you will get the maximum power levels. Nano generator, it is having power high power density, simple structure, low frequency, but we can't run long term reliability. Thermoelectric generator, there is no need for lighter movement. It is inexpensive, but it is going to give a low power source. Biofuel, it is compactness and sensing and power modules combined. No illumination RF signals are required, but the proportion of sunlight can be influence the power density. Okay, and the solar cell, it is flexible, light and wearable application appropriate and requires the light. The batteries provide the as much as possible, but a replacement regular charging is required. For your wearable application, it is rigid and hazardous. We have to think about that. The challenges. Okay, so limited power supply and the power efficiency. What is the energy harvesting? So while choosing any of the harvesting techniques, we have to think about this. Okay, so what is the challenges are in the power supply, energy harvesting, small form factor, sensor integration, user comfort, data processing and transmission, real-time monitoring. So all those things are in challenges. Here, one of this thing by using wireless detailing antenna geometry, they have done the transmission. And already know this voltage regulator we have known, and these are the one of the things control. And in this, different types of converters are LDO regulator, multi-phase regulator, pulse width modulation, and offline AC to DC, switch mode regulator, charge pump, and multiple output and converter relatively similar. So what is the LDO regulator? They call it low dropout regulator. Let's say if you have input voltage of 3.7, you want an output of 3.3. So at that time, though it is a DC to DC converter, the difference of input and output is very less. So it is called as a low dropout regulator. And multi-phase controller and pulse width modulation controller, all those things required for the DC to DC converters. Okay, and the switch mode also one of the DC to DC converter. And a charge pump. Let's say you have a 9 volt, but you have a device which need to be powered with around 48 volt, but which is going to consume less current, 1 milliampere. At that time, no need to go for an DC to DC converter. You can use simply charge pump. Mostly it will be used in the biomedical device, because for safer thing, because it can't deliver more current. So, but safer to be safe in the region for the patient, we can use a charge pump. Another is a multiple output controller and converter. Let's say they have a simple DC to DC converter, but input is going to be one, but in output you are going to get a different DC output voltages. Okay, And this is a step down, that is a buck. Step up is a boost, and step up or step down is a buck boost, right? So this is constant, whether it's going to input voltage lesser than the V out or more than the V out, the voltage is constant. And invert the negative output. Sometimes, let's see, if we take an op amp, we need plus or minus 15 volt. We can't have some two batteries, so we need to have some other converters to create a negative volt. That is, these are the things that are required. So all those things we have seen: power convert, power buck boost, all those topology we have seen. Now, what are the things available in the market? For example, let's say now these are the topologies. These are the topologies. We can't directly connect the inductor and switch directly connect. We can expect the output. So our thing will be like this. So this is a switch and sampling circuit, comparator, reference voltage, all those things going to control the element switch, right? So we need to have this complete system in the package. So that can be achieved by using some of the ICs. So for example, this is a DC buck converter power supply. We can have input voltage 3 to 40 volt, output voltage is 0.5 to 35 voltage. We can adjust this to get the various voltage, and output current is rated is 2 ampere, maximum we can go for 3 ampere, and switching frequency is 150 kilohertz, and it is a industrial grade, and we can work up from minus 40 to plus 85. Conversion efficiency is 92%, efficiency 90%. And this is one of the mini boost buck converter. USB output charges above the power module. Let's say it can be from 0 to 9 to 5 volt. Always output is a 5 volt, right? So that can be achieved by this kind of a thing. And this is a buck boost converter. Input voltage can be 3 volt to 16 volt, and we can adjust the output voltage 2.5 to 9 volt, right? So we can use this kind of a converter for our project. And sometimes you have to implement solar panel and charging the battery. So this kind of a panel we can buy. So we can connect a 6 volt to 24 volt solar panel, and if you have a lithium ion, this is 18650 lithium ion battery, and we can see that the micro USB output also going to get 5 volt, and charging cutoff more than 40 to 4.2 volt is going to cut off, and you can get this all those output from here. It can be used for the powering our IoT node. Okay, and what are the basic requirements required for IoT DC to DC converter? Let's say we can say that yes, I am going to use a DC to DC converter, but there are some requirements required, because here ultra low output voltage range. So we can't say that my DC to DC converter going to give only 12 volt, 24 volt. It can need to give 3.7 volt or 1.1 volt, depends upon the processor required or some other sensors required. And ultra low quiescent current. So when it's not operating, what is the current? Otherwise, for operation, what is the current is taken by a DC converter? Because already we know that we need to save the power from the IoT node. If it is a DC converter without working is taking then power, then it is a wasteful. Efficiency is going to decrease. And wide input range. So some of the things we can't forcefully ask the user to connect 12 volt or 9 volt. So we need to give the freedom to user. You can connect 6 volt to 12 volt. Like that we need to give it, and high efficiency. So whatever the input voltage and input power should be equal to output power in ideal, but we won't get, but the efficiency should be 95%. And it has to get in the small packages and space saving mounting. So whatever DC converter using should be very small, which can accommodate in the IoT node, right? Okay, now let's say we have done it. How to analyze? So there is a device. It is a key set. Okay, so by this we can monitor. For example, you know what are the processes going to do it. So it is, you can't with let's say if you connect a multimeter, you can't do it because sampling is very, very less. What is sampling? Let's say the power taken by the IoT node, you have to sample it for each time period. So if you take a multimeter, you can't take it for each millisecond or microsecond. That is, sampling is not possible. So why it is required? Because our transmitter and receiver not going to work for hours or minutes. It is going to work for milliseconds. Within millisecond period, we have to get what is the current taken by the IoT node. So we need to use this kind of an DC power analyzer, and we can know, yes, this is a sleep mode, this is the process, and you know what is the process is done by, because we will get, because we only programmed. right? So this is a maybe transmitter. This may be an sensing. This may be the processing. So this is an radio transmitting again happening, right? So these are the ideal pulses where the nothing is there. This is the sleep current. So like this, we have to analyze why it is required. Again, we have to find the average current. At last, we have to calculate the battery lifetime. That is important, right? At last, we need to calculate the battery lifetime. Okay, okay. Why? Let's say why all those things are required, right? Why all those things are, why buck converter, boost converter are required? For example, if you take an wearable device, okay, wearable device, you know, everybody's hand, we have a smartwatch. Then what are the things are available in the wearable device? We have touch screen controller and 3-axis sensors like 3-axis accelerometer, press and attitude sensor, heart rate sensor, and we have a Bluetooth, we have a memory, we have ARM microprocessor. But this is going to give, lithium ion cell is going to give 3.7 volt. Here, you can see here, the backlight requires more voltage, so that they have used the boost regulator. And again, charging the battery, you won't connect to 3.7 volt. You're going to connect a 5 volt, right? Then again, a battery charger. Then LDO. This requires only 3.3 volt, the sensors. Then you have to use a LDO. And this going to use again lesser voltage. Then again, you have to use the buck converter. And the GPS module, again, you have to use the buck converter. So even if you see, the small wearable device consists of different elements which requires different voltages. So we have to use a different power processor, otherwise DC to DC converter, right? So this is the how the powering of IoT is completed. Do you have any doubt on this? Any doubt? So it is already shared. I'm going to share the book, right? I'm going to share the book, and you can because these are not in the book. So this everything is in the book, right? These are everything is in the book. Previous to this, I'm going to share the book. You can. Do you have any doubt? Okay. Now we are going to see on case study. It is very interesting case study, right? While designing, what are the points that are considered, right? So this is not an. This is a good reference. Okay, it's a good reference for anything. Just a minute, I'll share my screen. Just a minute, it's opening. So here we can see. Are you able to see it? The screen?
Yes, sir.
Yes. Okay. Now we can see low power remote neonatal temperature monitoring device, right? We know that neonatal is the baby born, which in the within the 30 days they called as neonatal. After that they called it infant. So here, let's say if we want to monitor the neonatal baby, we can't have the accuracy of 2 degree or 3 degree or even 0.5 degree. We need to have 0.1 degree, right? We need to have a 0.1 degree of it. We need to have it. Okay, right? Then we need to think about why it is required. So according to WHO, all those references they given, more than 95% of deaths occur in the developing nations like Africa and South Asia. because they're not able to maintain the correct temperature. Okay, and the temperature should not go below 36.5 degrees Celsius. So 36.0 to 36.4 is a mild hypothermia, and below that is called moderate hypothermia, and it is goes below that is a severe hypothermia. So we need to maintain the temperature in premature baby and as well as the normal baby, which is affected by which is we need to be careful. And we know that we can't use a thermometer, and we can't use digital thermometer. We can't keep on the monitoring, and only for monitoring it we can't have a neonatal intensive care unit because it's very costly affair. Now this group, they have designed a temperature sensor, right, which is wearable thing, and is a baby, and it is kept it in the radiant warmer. So what are the things they have considered, right? Now, if medically, where is the temperature you are going to get the actual temperature? One is a tympanic, another is a rectal. That is nowadays, if you go to the pediatrician, they used to measure the ear temperature. That is tympanic. Otherwise, in nearby the forehead, they'll measure it. So another is a rectal temperature, but this cannot be used for the continuous monitoring, right? So one of that, and however, they found that the right quadrant, right upper quadrant of the abdomen is below the rib cage, is going to give the potential location which can give some accuracy in the temperature. And here they need to monitor with 0.1 degrees Celsius, right? That is also important. These are the challenges. And again, longer battery life. So at least it has to monitor 2 to 3 weeks. Sampling time is 15 minutes. Okay. For example, if it is 2 to 3 weeks, sampling time is 15 minutes. Per hour, it is 4. Per 24 hour, 24 into 4, it is 196. And if it is 3 weeks, 196 into 3. So 196 21, right? So one day it is giving 196 readings, and per 3 weeks, let's say 21 days, it need to go approximately 200 into 21, 4,200 readings it has to give, right? Then the battery reading should be low, and battery has to be withstand the 3 weeks thing. And now what is the challenge they're going to face? They have to use ultra power, low power design to meet the requirement of the longer battery, because they can't keep an lead acid battery or a bigger thing. They need to can keep on a neonatal baby button cell, that this type or all those things, which is going to give an 3 volt, right? And again, robustness, because this is not an adult, this is a baby. Then it is prone to the sweat, urine, fecuses, and washing, all those things, shock and vibrations. So all those things need to taken care, right? So that are one of the things. And they have compared some of the relative work, and they may mention only 48 hours, all those things they have done. And here, system design, right? System design, what are the things they have used? Though there are a low power wireless communication, Bluetooth, Bluetooth Classic, ANT, Zigbee, Wi-Fi, NIC Plus, IRDA, they have used the Bluetooth for this, right? They have used the deploying the Bluetooth, and for short range wireless communication they have used. And here, this is the block diagram of a temperature sensor. So what are the things are containing? This is the inverted F antenna 2.5 GHz. Impedance matching is done. This is the antenna. The patch antenna you can see in Bluetooth devices, and this blonde filter. And here we have CC250, which is acting as a microcontroller, which is having an ADC, and again a Bluetooth stack also involved in this. And for measuring, they have a thermistor. Thermistor is going to give the change in resistance according to the temperature. So the change in resistance has to convert into the voltage. They need to have analog signaling circuit. They have the analog front end, and here for crystals and 3 volt battery coin, and we need to program and the status what is doing, whether its battery is low or transmitting or sensing, whatever, we need to have some status LED, right? And to communicate with the gateway, now this is an IoT device. This is a node which is attached to the neonatal baby, and this is an Raspberry Pi, the gateway device, which is getting the signal from this and is going to send the data to the cloud, right? This is a Raspberry Pi, and this is the top view and bottom view of the sensor, right? And the sensor platform, they have again they have chosen what is the current taken by the sensor, what is the current taken by the processor, everything they should know, right? They should know about this. And for security also, they need to know 180-bit hard AES support and Yatana selection and performance. So reduced efficiency, and we have to check that small put some critical parameters, shorter range, smaller useful bandwidth, more critical difficult tuning. All those things are very challenges they have done, and they have used the inverted antenna, right? And they have these are the chip antenna and IF inverted. So what are the range and meters they given, and what is the efficiency also they given, right? What is the cost? Now, main thing here, you can see here, they need to convert a change in resistance value to change in temperature is going to give the change in resistance. Again, change in resistance has to convert into change in voltage. So they have used the voltage divider. So this is a fixed resistance. This is a fixed resistance. This is a thermistor, negative temperature coefficient. If temperature increases, the resistance is going to decrease. Now, you can ask why they have used 0.1% tolerance. Because if tolerance is more, then what is going to be achieved? If tolerance is more, we can't say it is 10K. If it is 5%, it is going to be 9,500 to 10,500 ohm. So we can't exactly see that what is the temperature. So we have to use less tolerant resistor, right? And they have done this, all those things, calculations, and at last they have saying that there will be an for R1, del R1 it will be 10 or 10 ohm and plus or minus 2 ohm due to the temperature change in the 1 LSB ADC, which is 10 ohm in the 25 degrees Celsius, 5 ohm in the 40 degrees Celsius. So it is correspond to 0.3 Celsius error margin. So if it is measured 30, let's say 36 degrees Celsius, it may be 36.03, and otherwise 36 35 means 35.03 or 34.97. So we achieved plus or minus 0.1 accuracy because the change in is in another order, right? So it is possible, right? And they also made this thing to go into the sleep mode by using the programming. So they also analyzed what is the sleep current, what is the conventional, and they have a new circuit, active mode and sleep mode, and conventional thing, what is the current they taken. Now we have to keep the sensor. So the sensor we can't keep the directly on the body of the neonatal baby, right? Then it has to be placed on a aluminum cup, which is again, which should not cause any of the infections, or it should be cause some allergic allergic thing to the skin of the baby, and it should be thermal conductivity also. They have done an aluminum cup, right, and kept on the sensor, which is having more high thermal conductivity and is a glow. So at last they made a like this, right? So this mandrel prototype, and the power switch also given to initiate the connections, and when it is pressed and held for three things, and for 5 seconds it is going to have. And for different baby size, they have a belts to wear it, belt design also, right? And a baby friendly design. It should be baby friendly, and they have done some experiment how it is going to there. Let's say if it is dipped in water, how it is going to make, and they have changed the temperature with controlled environment, and 10 hours also it is giving the value. And the responsiveness, the results, it is an evolution experiment setup they are given, and they're given 40 minutes within plus or minus 3 degrees Celsius, and the Bayer reference package, these are the responsive time. Let's say it is going to take 3 minutes, 4 minutes, 4 seconds. So directly the sensor is going to give 4 seconds, and if it is reference is going to do 3 minutes, and package is going to give 4 minutes. So it is going to reach the value. And initial one-time advertising mode and periodic data transmission. So it is one time it has to say yes, I'm available, and what is the current taken. So here the peak current is, the sleep current is 1 microampere, and on time is 0.899 seconds, and data transmission is going to have an 1 second, and initial advertisement is 180 seconds, right? So what is the at efficiency of 90%, what is the millijoule is consumed from the battery? And they have done the accuracy also, accuracy also within the range 0.04 degrees Celsius. They have measured from 25 to 40 degrees Celsius. And power consumption, they have used the Agilent multimeter and transient current, and they have measured through an Tektronix oscilloscope, and they have found that 3 volt CR202 kind battery with 225 milliampere can 96 data cycles for every minute. It is going to consume this amount of power, so it can come, the battery lifetime is around 388 days, about a year, right? So these are the things we have to consider. So it is a typical medical IoT device. So accordingly, we have to design. Let's say if it is industry IoT, we have to consider some of the temperature range and vibrations, all those things in the industry. So accordingly, we have to consider this. Okay. Do you have any doubt on this? Do you have any doubt? Do you have any doubt?
No, sir. No, sir.
No, sir.
Okay. Yes, almost we have completed this one. Maybe from tomorrow onwards, we will see the IIoT classes, reference classes. Every week we need to have 2 classes, right? So we'll have this, we will revise all the IIoT courses. Okay.
Okay, sir.
Okay, sir. Thank you, sir.